Complex numbers. Perform combinations involving complex numbers. Some functions have zeros that are not real numbers. The complex number system is used to find zeros of functions that are not real numbers. Okay, so complex. Whenever we think about a complex number, we think about what? Let's say 3/4 divided by 100 divided by 150. That's complex, right? Because it's a fraction within a fraction within a fraction. All right, so in this section, we're going to talk about the types of complex numbers that are not real numbers. They exist, but they're not real. So my best example to you is whenever we look at a Cartesian coordinate and we look at the XY graph and we draw these parabolas or we draw a straight line. Okay, so we're talking about two dimensionals. But what if something out here happens? What do we got going on? Now we got a 3D. Another one example, and this is not a good drawing, my apologies. Let's call this the Earth. It's not a very good circle. Say we have this radius that goes into the center of the Earth, and above it, so many miles, is this satellite floating around. So here we go. We have this triangle involved, and my apologies, guys. I have to practice my drawing a little better. But anyways, we have this distance between the Earth and the satellite going on. So there's not a line there, but there is. So we're going to call this imaginary. So in this section here, whenever we're talking about imaginaries, we are also talking about roots. Well, we agree the first root that we know is a square root. We don't write the 2 here. It's even root. And then we have a cube root. We have the fourth root, even root here. Fifth root, and so on. Now, these two are odd. I know that I can multiply something an odd amount of times and my answer will come out to be negative. We know that, right? However, if we have an even root, that means we're multiplying it even amount of times. Well, it's not going to come out to be negative. There's no way that that would be a -1. It ends up being positive. So if I have a negative radian, so let's talk about what it's a radian. So we have this nth root. I'm going to put n here because it could be any root. This actual house looking thing is called a radical. What's inside here is my radican. Okay, and it could be raised to some power. The whole thing could be raised to some power. But if my radican is a negative number and it's in an even root, then we're going to come out with something that's not real. We're going to call it imaginary because of this simple fact. You cannot multiply something even amount of times, come out with a negative answer. However, if it was an odd root, then it's going to be a real number. So let's talk about some more examples. So here we go. A says we have a square root of -7. Well, 7 is prime, so there's no factoring 7 down. However, I can rewrite it as square root of -1 times square root of 7. Well, what happens? The square root of -1, we're going to call it imaginary. And I'm going to put in its place I, and it's going to be multiplied to the square root of 7. Guys, you could put that I behind that square root of 7, but you got to be careful that you don't accidentally tuck it in that root, because if you do, it becomes an incorrect statement. So let's talk a little bit about I. I know I to the first power, right, gives me what? I, right? Because if I said 7 to the first power, it gives me just 7. I squared gives me negative. No, because it's even, it gives me -1. Well, let's talk about that. If I had the square root of -1 and I want to undo the root, I'm going to raise it to the power of 2 because it's a square root. If that was a cube root, we'd raise it to the cube power. When I do that, now I have -1 raised to 2 over 2, which is 1. So my answer is -1. Makes sense. So if I have this I squared, I get -1 as my outcome. Let's talk about I cubed. It is odd, so I'm going to get -I. I to the 4th gives me +1, and this repeats. So every 4th one, I get a +1. So knowing this, let's go ahead and do B. B says we have the square root of -16. Well, it's a square root, and I know that I can pull out the -1, right? Because it's -1 times 16. But I also know, and if you want to leave it as 16, you can, but I also know that 4 times 4 gives me 16. I also know that this can be written as 4 raised to the 2nd power. Now, there's multiple ways to look at this. You don't have to do it this way, but sometimes you don't always know what's the square root of something until you break it down. Well, now I have this root here and this power, and just like what happened up here, the root and the power are the same. They reduce down to 1, and it leaves me with, and this here turns to I. So I times square root of 4 squared reduces down and leaves me with the rectangle. So a 4i, or you can write I4, 4i. It's multiplication, so this order doesn't matter. It's just how you notate it. Like in this example, you do not want to put it in the root. All right, let's talk about D. Or no, let's do C. C says I have -1 times that root. Well, 13 is prime, so I know it's not going to factor out. However, I got this -1 inside the root. So I'm going to factor it out as I. Let me get my pencil back. Sorry, guys. Here we go. Let's get our pencil back. I'm going to factor it out as I, and then it's going to be multiplied to that square root of 13, because 13 don't factor out. So -1 times I is -I square root of 13. Now, 64 is not always as obvious. And my apologies, the computer is acting up on me. There we go. So it's not always as obvious, so let's do D. Let me clean this up just for a second, so I have some space to do the last two. Well, if you notice, D has the -1 multiplied by the root. So I know I'm going to have -1 on the outside, right? So let's go ahead and put it on the outside. Now, I look inside this root here, and I got square. Let's go ahead, square root of -1 times square root of 64. Let's go ahead and convert the square root, or factor it down, of -1. We know that it's going to be I. Now let's talk about 64. Can I factor it down? Well, I know that 8 times 8, and what happened? Let's talk about that just for a second. Whenever we have a square root of whatever number is inside it, we all know square root of 4 is 2, but how do we know it? We know that this is a square root, meaning that when I break down this 4, I need to have it in a group of 2. If it was a cube root, then I can break it down in a group of 3, right? There has to be 3 in there, and this one works out, right? 2 times 2 times 2, which gives me a cube root of 2 cubed. See where I'm going with this? But since it's a square root, I needed to have a group of 2's, or not, the number don't have to be 2. I just have to make sure that it could have been 3 times 3, which is 3 squared. We just need it to be a group of 2 or even number to factor it completely out. So we'll just have to practice on these and do more of these. I know it might be a little confusing, but let's just reach out to me if you have any questions. So let's do this. So I know that 8 times 8 gives me 64. You may not knew that. You may have said, oh, I need to factor it down, make the factor tree, or you want to do division. You could have done that and kept it going. So then you said 64 is 2 and 32. Well, 32 is not prime, so I need to continually go on. I know that 2 goes into 32 16 times. I know 2 goes into 16 8 times. 2 and 4, and then 4 breaks down. Now it's a square root. I need to make sure that I put everything in groups of 2s. The base is going to be 2s. So what I got factoring, I got 1 group of 2, 1 group of 2, and 1 group of 2. So I'm able to say, oh, okay, well, I got 2. And y'all, I'm doing extra steps. You do not have to do this. I just want you to see it. That square root of squared gives me 2. That square root of squared gives me 2. That square root of squared leaves me 2. So I'm left with the radican here. And it's all times 1 times -1 times the I. So it's like this. So my answer is. Okay, now there's multiple ways of doing it. I'm just breaking it down. You do not have to do this much work. All right, so let's do E right quick. E is 48. It wasn't as obvious as 8 times 8, for 64. However, I do see that out here is just a positive 1, so I'm not worried about that because it's not changing anything. But in here, I do have a square root of -1 times that 48. Well, 48, you could try 2, you can try 4. I'm going to try 2 because it's a prime factor. I'm trying to see what I can factor out of this root. 2, and if you need to, guys, just do your division. 2 goes into 4 2 times. 2 times 2 is 4. Subtract 4 minus 4, bring down the 8. 2 goes into 8 4 times. So now I got 24, right? Now I could break this down. I know 2 goes into 24 12 times. And I could break 12 down as 2 goes into 6. And then 2 goes into 3. Now, it is a square root, so I need to make sure that I have groups. And in the groups, there must be 2 of the like bases. And I do. I got this. But that 3, I only have 1 3 here, so I can't group it with nothing. So what do I have here? And you could say 4 and 4. I mean, you could go 4 times 4 times 3, or you could have wrote it as 2 squared, 2 squared. It doesn't matter. We know that square root of -1 is I. Square root of 4 is 2. Square root of 4 is 2. Square root of 3, it stays behind. Now just clean it up. I times 2 is 4I. Square root of 3. In the next slide, you just check your work. There's more than one way to solve these. All right. So if you have any questions, again, just holler at me. Let me get to our next slide. All right, so complex numbers is a number of a form of, and this, it shows A plus BI, where A is the real numbers, and BI is going to be the imaginary part. All right, so it's important that you write the real number first, plus or minus the imaginary part. If A is equal to 0, then all I have is an imaginary. If B is equal to 0, then all I have is a real part. Okay, so here you go. In order for us to have an imaginary number, A and B cannot be 0. Well, if, again, A could be 0, and it just leaves me with just strictly the imaginary part. But in this section, it's telling you that neither one can be 0. Okay, so a pure imaginary. So here's the difference. A pure imaginary. That means that A is going to be real, but it can equal 0, leaving me with just the imaginary. As long as BI is involved and it's not 0, then we have a pure imaginary. But if B is equal to 0, then we have 0 times I, which is 0, so there is no imaginary. That makes sense? Okay, complex numbers obeys a commutative, associative, and distributive laws. Okay? We add or subtract them as we do binomials. We collect the real parts and imaginary parts of the complex numbers just as we collect terms in binomials. Okay, so commutative, associative, and distributive laws. let's talk a little bit about these by actually applying it in an example, okay? So here we have two binomials, right? And we're adding them together. Whenever you add or subtract, you can only put together like terms. So I'm going to make sure, and my answer is going to be written as the real plus or minus the imaginary part. So I'm going to pull out all the real. So I got 8 and this plus sign, and that 3 is positive. If you want to put it in parentheses, you can. You can bring down a plus. And then I have a positive 6i plus a positive 2i. So those signs don't change. Now I got 8 plus 3, which is 11, plus 6i plus 2i is 8i. And that's my answer. However, when we come over here and look, I got this negative sign separating the two binomials. So this means when I distribute the negative sign to everything in this parenthesis that follows it, remember, whatever follows the negative is where it's going to be distributed. It's going to change everything. So what I'm going to do is I'm going to pull out the real. So I got 4, and then I have negative 1 times positive 6 gives me a negative 6. I have a positive 5i. And again, if you want to use parentheses, go for it. Plus, actually, it's not plus, it's minus a negative 3i. And I'm just going to rewrite it this way. I'm going to do an extra step. You don't have to. 4 minus 6. Well, that's like saying I have $4, but I spent 6, so now my bank account's in a negative 2. I have negative times negative, so now I have positive, right? Because negative times negative is positive. I have 5i plus 3i gives me 8i, and that is my final answer. So you can see the next slides where it shows you how to work it. Let's go back. Let's see. So this one here says when square root of a and square root of b are real numbers, then we're going to get these two together. Because the roots are the same, if you're multiplying and the roots are the same, I could just put the radicals in under the same root, okay? I said this is true when a, square root of a, and square root of b are not real numbers, right? So if we have a square root of a negative number, we end up with -1, right? So now let's talk about multiplication here. We're multiplying and the roots are the same. So what I'm going to do is I'm going to acknowledge that I have a -1 times that square root of -16, square root of -1 times square root of 16 times square root of -1 times square root of 25. Now, some of you already know what's the square root of 16. We know what the square root of -1 is. It's I. Square root of 16 is 4. Square root of -1 is I. Square root of 25 is 5. And if you need to factor it down, I encourage it. Now, let's put these together. I got I times I, right? Whenever you multiply like bases, we add the powers. In this case, they're raised to 1. And then I got 4 times 5. I squared gives me back -1. So now I have -1 times that 20. So it's -20. Now we have binomials, multiplication, right? So in multiplication, we're going to use the distributive law. We're going to go 1 times 1. And if you want to write extra steps, you can. You can use the full method since it's binomial times binomial if you want. Plus 1 times 3i plus 2i times 1 plus 2i times 3i. So 1 times 1 is 1 plus 1 times 3i. So 1 times anything is just whatever you're multiplying it to, right? Now let's look at the last part. I got 2 times 3 is 6. I times I is I squared. Let's combine these two middle parts together because they're like terms. So 3i plus 2i is like saying I have $3 and I get 2 more, so I have 5i. Now let's rewrite the I squared. We know it's -1. So now I have 1 plus 5i. Positive times negative is negative. And now let's put the real parts together. I have 1 minus 6, meaning I have $1 and I spent 6, so I'm in the whole 5. So my final answer is -5, -5. -5 minus 5i. So I'm going to clean up a little bit here so we can do the next one. Here, let's just go to let me scoot the slides over. There we go. Oh, well, I'm going to have to erase it. It won't let me just scoot the slides over. So let's make some room. Let's do C. All right, so I kind of cleaned it up a little bit better. It was a mess. All right, so now on C, I see that I have this binomial raised to the power of 2. What does this tell me? This tells me I have 2 of these parentheses. They're identical. Now there's a shortcut, guys, you can do, but I'm not going to do the shortcut because I want to show it to you right quick. I'm going to take the first times the first. So I'm going to say 3 times 3. And then I'm going to distribute the 3 to the other parentheses. I'm going to put a plus sign. 3 times -7i plus -7i times 3 plus -7i times -7i. All right, so now when I go clean this up, I know I got 3 times 3 is 9. I got +3 times -7i is a -21i. I have -7i times a +3i, or excuse me, and -7i times 3 gives me a -21i. And now I got negative times negative, which is positive. 7 times 7 is 49, and then I times I is I squared. Excuse me. So now that I have this, I have the middle terms that stay. I keep the imaginary, right? Because they're like terms. I have -21i minus 21i. So I'm in the whole $21 and I spend 21 more dollars. So I'm actually in the whole $42. So I'll put the I with it. Bring down this 9. And then I know that I squared is going to be -1. So now I have 9 minus that 49 minus 42i. So what I did is I just took these two, multiplied together because positive times negative is negative, and moved it up here with the real part. Now let's finish. I have $9 and spent 49. So I'm in the whole $40. And bring down the imaginary part. And that's my answer. And again, you can check these. The next couple slides are worked out. And there's a shortcut. It's actually showing this to you here. It's telling you that if our parentheses, our binomials, it has to be binomials, are identical. So what you're going to do is take the first term in each parentheses and square it. And then we're going to take the sign, which in this case is negative, put it right here, double the middle. And what is the middle? It's going to be 3 times that 7i. So 3 times 7i, and we doubled it. And then we're going to square the last part. So this is if and only if the binomials are identical. Signs have to be the same and everything. So that's a shortcut if you would choose to use it. Here is just talking about what I talked about earlier. It says I raised to the first power is equal to square root of -1, we know is I, right? Says square root, or I squared is -I. So what they did is they did this backwards, where earlier I told you that if I had I squared and I wanted to undo the square root of -1, I know I square both sides. Okay, so this here is just another way of looking at it, and it's letting you know how to repeat the process. Okay, so what if you had I cubed? It says that is the same as saying I squared times I. Remember, if you multiply like bases, we add the powers. So I got 2 plus that 1 gives me back my I cubed. This is actually -1 times I, which is -I. That's how we came up with the I cubed. I to the 4th is just saying that I'm going to take my I squared, which we know is -1, square it. Well, if we square it, that negative becomes what? Positive. They have a typo here because I raised to the 4th is +1. Because if I square that negative, it becomes positive. Okay, so now I to the 5th is I to the 4th times I to the 1st, because I know if I add those two together, it gives me the 5 back. I squared is -1 times I. And then 1 times I gives me my I. You notice it's going to repeat. So that means I to the 6th would be -1. I to the 7th would be I to the 8th would be 1. So it's just repeating itself. So let's try to figure this out. I know this here already gave you the work and the answer, but let's just look at it. 37. I got I raised to 37, and I'm going to write it as a factor of 4. So I know that I to the 4th, and whatever power I raise it to, needs to get me close to 37. I know that 37 is not a factor of 4, but I do know that 4 times 9, right? So I'm going to rewrite that. It's a little messy. 4 times 9 gives me 36, leaves me with 1. So they went about it a little bit different. They said we can do 2 to the 18th. You could do that if you want to as well. But I like to use 4 if possible, because what is 4? I to the 4th is 1. Let's make it easy as possible. So I to the, or 1 raised to the 9th power is just 1. 1 times I gives me I. Let's look at 58. 58. I know 2 will go into it. They showed you 2 goes into it 29 times. But 4 times what gets me close to 58? Well, if you have to, do division. Make sure that looks like division, not a root. All right. So, whoops, I did it again, guys. I'm getting carried away here with the root. So let's see. And I like to use 4. If you want to use 2, you go right ahead. But I like to use 4. 4 goes into 5 ones. 1 times 4 is 4. 5 minus 4 is 1. Bring down the 8. 4 goes into 18 4 times. 4 times 4 is 16. 18 minus 16 is 2. What do I have to do? I got to tack on a decimal, right? Bring down a 0. So what does this tells me? Well, let's check it out. What is 4 times 14? We know 4 times 4 is 16, carry the 1. 4 times 1 is 4, plus 1 is 5. So this tells me that 4 times 14. Now this decimal told me that it didn't go into it clean. That means I'm going to have a remainder. I'm going to have some stuff working over. So if I wanted to finish this up to see what the remainder is, and y'all, my apologies, this is a 6. I'm going to say 4 goes into 20 how many times? 5. 5 times 4 is 20, and I get a remainder of 0. So I know this next part, so bear with me. So if I rewrite this I to the 58 as I to the 4th raised to 14, 4 times 14 is 56. 56 minus 58 leaves me I squared. If you're unsure, let's do it again. 4 times 4 is 16. Carry the 1. 4 times 1 is 4, plus 1 is 5. That's 56. 56 minus 58 leaves me with 2. Okay, we're good. I to the 4th is 1. I squared is negative 1. Now 1 to the 14th is just 1. 1 times negative 1 is just negative 1. So I did extra stuff, so you don't have to. So there's 2 different ways to solve this here. You choose the one that's best for you. All right. So now let's talk about conjugates. So if you have to remove I from the complex number, and I'm going to dig into this a little bit more. I just want to talk to you about conjugates. Then I know that I need to multiply and make sure it's in the real plus or minus imaginary. I know I need to multiply by the opposite sign. See it? What happens? So let me show you. If I have negative 3 plus 7i times negative 3 minus 7i, and I say, okay, first times first, so I get negative 3 times negative 3 plus 7, whoops, I need to scoot this down a little further. Sorry, guys. Negative 3 times negative 7i plus, now let's go 7i times that negative 3. And then positive 7i times a negative 7i. Now let's clean this up. I got negative 3 times negative 3 is a positive 9. I got negative 3 times negative 7. We got this plus sign here, so is a positive 21i. I have a positive 7 times negative 3i, or excuse me, positive 7i times negative 3 gives me a negative 21i. And then I have a positive 7 times a negative 7. What happens? I get a negative sign here. My apologies. I kind of jumped the gun there and put the positive. And I saw the answer because of that I squared, but we'll get to that here in a minute. All right. Now I have 7 times 7 is 49, and I times I is I squared. What happens? This middle goes away because I have a positive 21i minus 21i. It goes to 0, leaves me with 9 minus that 49. I squared is negative 1. So negative times negative is positive. 9 plus 49. So what do we got? 9 plus 9 is 18. Carry the 1. 9 plus 4 is 36. Plus 1 is 378. So conjugate, meaning that we have to multiply by what's going to undo the or cause the imaginary part to go away. So let's do that. Let's use this example. If you notice that the first in each binomial are the same, and the last in each binomial are the same, but the signs are different. That means I'm going to take, and I'm going to do this a shortcut. You do not have to do that. You could actually do this distributing if you wanted. If you wanted to, we would have this. And I'm going to write it out for you just in case you choose this method. I'm going to show you the shortcut. Okay, that's if you distribute the first to the first and, you know, just keep distributing. All right. However, if I notice I have a binomial times a binomial and the first and last terms in each one are the same, but the signs are opposite, then I know I'm going to square the first term minus square the second term. What happens? The middle goes to 0. Because now I have negative 35i plus 35i. It went to 0. All right, so 5 squared is 25. Bring down the minus. 7 squared is 49. I squared, well, I squared is negative 1. Negative times negative is positive, so I got 25 plus 49. So now I got 5 plus 9 is 14. Carry the 1, 6, 74. Okay. Now on this one here, it's just a monomial times a monomial. I have a positive times negative. So I got negative, right? 8 times 8 is 64. I got I times I is I squared. So now I got negative 64 times negative 1. Negative times negative is positive, leaves me with 64. So if you want to, you can check this work. The slides have the examples. Now let's talk about dividing. So we read it this: 2 minus 5i divided by 1 minus 6i. Whenever we talk about fractions, we cannot have multiple things in the denominator. We cannot have 0 in the denominator. We cannot have I. We cannot have a fraction. We cannot have a decimal. We cannot have a negative sign. We can't have a root. However, these here has a operation rule that we can apply to undo that. 0 does not. If 0's in the denominator, it's undefined every time. Okay? So this is where the conjugate part comes into play. If I multiply this bottom by the conjugate, see the signs changed, then I'm going to cause the I to go away, go to 0 in the denominator, and that's what we wanted. However, what you do to one part of this fraction, you have to do to the other. You can't just do it to part of it. So now let's do this. So on top, I'm going to have 2 times 1, 2 times 6i, plus a negative 5i times 1, plus negative 5i times positive 6i. All over. Now, if you want to do the shortcut, you know that it's going to be the first term squared minus the second term squared. However, if you need to do the extra steps, do it. It'd be 1 times 1 plus 1 times that positive 6i plus that negative 6i times 1 plus negative 6i times 6i. Now, if you need that, do it, okay? Now let's clean this up. So now on top, and when I clean this up right here, just in case you want this step here, guys, I'm going to clean this up for you. Okay, so I'm going to stay in track. So if you choose this method, I'm going to do both of them for you, okay? So now 2 times 1, 2 times 6i, and they're both positive, so it's positive 12i. I have a positive, negative. Positive times that negative is negative 5i times positive 1 is a negative 5i. Then I have this positive times that negative 5i times a positive, so we know it's negative. And then I have 5 times 6 is 30, and then I times I. On bottom, I have 1 squared is 1 minus 6 squared is 36, and I squared. All right, so if I was to clean this up, oh, I left my, because that was 6 times 6. It should have been 36 here, guys. If you caught that, thank you. So now I have 1 plus. What happens? The positive 6i minus 6i goes to 0. Leaves me with a negative 36i squared. And I'm just going to rewrite this. And what do I know about I squared? So let's plug it in and clean up these two terms here because they're alike. So I have a positive 12i minus 5i, saying I have $12 to spend 5. So now that I have 7i minus 30, well, I squared is negative 1 all over 1 minus 36 times negative 1. So that's what we got here. Okay. So I'm going to finish up down here instead of right here. So we're at the same point now. So now I have 2. Well, this negative times negative is positive. I'm going to bring it to the front because it's a real number. So it's going to be a positive 30 plus that 7i all over 1. Negative times negative is positive plus that 36. Now I have 2 plus 30 is 32 plus 7i all over 37. Now we're going to rewrite it as real plus or minus imaginary. So I have 32 37ths plus 7i 37. And you can write the I out to the side. or on top. Just make sure it don't go in the denominator. So this is real plus or minus the imaginary. Oh, and always reduce, guys. Always reduce if you can. And you notice this next slide has our answer. And that ends it.